Good afternoon, this is Schweitzer, and we're doing a series of videos walking ourselves through pretty much everything we want to know for acids and bases. In this case, our main objective here is, can I determine the pH of a weak acid? And we'll be introducing and using some of the concepts we've used earlier, but essentially let's do an example of this. Alright, let's say I have HF. HF is a weak acid. So it undergoes hydrolysis and it produces H3O plus ions and F negative. Now, if I were to do initial stoichiometric ratio ending table, I call it an ICE table, and let's say I have a 0.1 molar of this, how much product do I get? Well, a typical chemistry student would say, well, this is going to go down to 0.1 and 0 plus 0.1 plus 0.1, and we get plus 0.1 here, and therefore the negative log of 0.1 is 1. Okay, but this thing ends up having a pH that's closer to 2 or 3. And the question is, well, why? Well, it turns out this thing also has a reverse reaction that says, okay, some of those H2 plus ions react with the F negatives, push back towards products. So we don't get a situation where we go to completion. So I'm going to erase this because it is not correct. Alright, so if we have 0.1 of these guys, I know that I'm going to lose some of it, but not all of it, and the question is, how much do I lose? So scientists, of course, are trying to quantitatively give it a number so I can figure out how much what I'm going to get. And they use, for all forms of equilibrium, what's called a K value. It's called an equilibrium constant. I talked about this briefly in a previous video, but essentially it's a way for scientists to track concentrations. So it's ratio of concentrations of products over the concentrations of reactants, and you'll see a little more in detail how that works out. But in this situation, I have the concentrations of reactants, concentrations of products, and I have this sort of gauge here. Turns out that for acids, weak acids, the Ka value is extremely small, which means that I have predominantly more reactants. If my K value were at the level of 1, then I would have equal amounts of both the numerator and denominator, or when I get to my stalemate, which is the equilibrium, I would have like 0.5 and 0.5. But in this case, weak acids don't have that. In fact, for HF, the Ka value for hydrofluoric acid is 6.6. Now I call it Ka because I'm dealing with an acid. The A doesn't mean much other than the fact that it's telling you, by the way, this is a hydrolysis equation of an acid. It is 6.6 e to the negative 4th. That means when I take the concentration of my products divided by the concentration of my reactants, I get 0.00, and it's to the negative 4th in case you can't read that, 0.66, that fraction. So really, for this to be this small, I have to have lots and lots of reactant, not so much product. And I get a fractional amount that's 0.0006. Okay, so we know we are going to be reactant favored. Okay, when we get to our stalemate, which is probably seconds after you were to mix HF with H2O. Alright, a couple things you need to be able to do here before you can solve this. First things is we have our Ka equilibrium expression. Okay, this is, I've described as being this. It's a tad more complicated, not a lot. What you do is you take the concentrations of your products, so my Ka value equals the concentrations of my products, that's H2O plus ions, and I raise it to a power of the coefficient, which happens to be 1, times the concentration of F negative to the first power. These are my two products. Obviously, I have more than one. I multiply them. Okay, it's not obvious, but that's what we do. And then I have the concentrations of my reactants. HF concentration, again, HF bracket 1. Now, it may not seem obvious to you, but water is a liquid, and liquids don't have a concentration. So in all of equilibrium, every branch of it, we are essentially tracking concentrations. Well, what if something doesn't have a concentration? What's the concentration of water? It's only determined by its density. So that being said, it really doesn't have a concentration. And if it does, but it doesn't change. The concentration never changes. Water concentration will be water's concentration. So things that are pure substances, like liquids or like solids. What's the concentration of this laptop that I'm writing on? It doesn't have one. Okay, they have a composition, not a concentration. So in this situation, we do not include, all right, we do not include liquids because they don't have a concentration. This is determined or was described as being the Ka expression. These are all the concentrations at equilibrium. Okay? So with that being said, that means anytime I get a concentration at equilibrium, I can just plug it right into this expression. Okay? All right, so let's solve this problem and determine the pH of this weak acid. Now, I stress to kids all the time, what I've described here is kind of different. It's more different than complicated, in the sense that the first time you go through this calculation, it seems quite different or quite complicated, but you do it a second time and you'll find it is exactly the same. The third time, exactly the same. Fourth time, exactly the same. And eventually, it's just the same calculation over and over and over again. So let's show you how it works, and then you can give it a try on your own. We'll try some examples. All right, so first of all, water will not play a role, so I put a dash there. Why? Because it doesn't have a concentration. I will then, because I don't have any of my product, in order to reach a balance, I need some of each. It's kind of a requirement for being at equilibrium. I need some of each. Minus, now I don't know how much I'm going to lose, but I'm going to lose some of this. But I do know, stoic ratio-wise, whatever I lose of X, I will gain of H2O plus ions, and I will gain of the F negative. I have to lose that because it's a 1 to 1 to 1 to 1 ratios. If there was some 2 or something there, I would have to have 2X. And then I do know that 0.1 minus X is what I would have at the end. And I do know that I would gain X and X. And at this point, it becomes a bit of an algebra problem. Like I said, all of these guys end up being put into the expression. My Ka value, which is 6.6 e to the negative 4th, equals the concentration of the acid is X times the concentration of F negative, which is X over 0.1 minus X. Okay, I need to know X. How much do I lose of HF so that I can determine, so that fractional values equals 6.6 e to the negative 4th. Now, I'm going to show two ways to do this. Okay, first way is sort of a long way, but really not that long, but would not be required on an AP exam, and that involves a quadratic equation. I take the 0.1 minus X, and I take 6.6 e to the negative 4th times 0.1 minus x equals x squared. Multiplied across, I get 6.6 e to the negative fifth minus 6.6 e to the negative fourth x equals x squared. At that point, I would solve everything over to one side. I get x squared plus 6.6 e to the negative fourth x minus 6.6 e to the negative fifth, and this is a quadratic formula, and you could plug it into a quad solver and solve for the root answers. And at this point, one would make sense and one wouldn't. The one that would make sense would likely be x has to be smaller than 0.1, and the other one, the value would be bigger than 0.1. Okay, and let's try it out here once. I have a quad solver in my calculator. All right, so my quad form, a equals 1, and then b equals 6.6 e to the negative fourth, and then c equals a negative 6.6 e to the negative fifth, and I'm getting, in this case, okay, 0.0078. All right, so x equals 0.0078. So now, once I have that, okay, then I'm going to put that here, then this equals that. That is, in the end, my H plus ions. And of course, negative log of 0.0078, and I get the pH of that value, negative log 0.0078, and I get 2.1. Okay, now that's not horribly difficult, especially if you have a quad solver. But on the AP exam, you're not required to have a quad solver, so, or they don't want it to be a disadvantage, they do it a little differently. So now I have 6.6 e to the negative fourth equals x squared over 0.1. Same thing I had is right here. Minus x. Okay. Now what they do is they do what's called a shortcut. Okay. And it is based on the fact that as I dump my HF in and I approach equilibrium, the amount that I actually lose is absolutely tiny. And you might remember from a previous video that when I drew the picture out of HF, I didn't even draw any H plus ions. I just drew HF, 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 and HF, because the amount that actually makes it to the product is quite small, especially relative to a 0.1. So they're saying that this number is very tiny compared to the 0.1. Therefore, mathematically, I could get away with just saying 0.1 minus x is basically 0.1. So let's solve it out that way. I got 6.6 e to the negative fourth times 0.1 equals x squared. 6.6 e to the negative fifth equals x squared. Square root both sides, and I get x equaling what? The square root of 6.6 e to the negative fifth, and I get 0.0081, and at that point that equals my concentration of H plus ions. It also equals the concentration of my happens to be fluoride ion, but at this point in our study of acids and bases, we're only concerned about the H plus ions, and the negative log of that value is 2.09. So this one gave me 2.1. This one gives me negative log of that value is 2.09. Not a whole lot of difference. And that is why the shortcut is used predominantly. Now, as the Ka value gets bigger, that would mean the change would get bigger. On my ice table, this would get bigger, and therefore x gets bigger, and therefore it starts to cause problems. As a general rule of thumb, as long as we're in negative fourth or smaller, then my x value will be small enough that I can use my shortcut rule. Either way, let's leave this video for now, and we'll try some practice examples on the next one. All right, thank you very much.